Hi everyone, in this recording we'll be going over vectors and dot products. Our goal is that by the end of this presentation you'll be able to find the dot product of two vectors and use the properties of the dot product, that you'll be able to find the angle between two vectors and determine whether two vectors are orthogonal, and that you'll be able to write a vector as the sum of two vector components and use those vectors to determine the work done by a force. In the last section, we studied the two basic vector operations, vector addition and scalar multiplication. So each of these operations yielded another vector. In this section, we'll be going over the third vector operation, the dot product, and this operation will yield a scalar rather than a vector. So we'll get one number as opposed to a vector with multiple components. So for the dot product of two vectors, if we're given the vector u with components u1 and u2, and the vector v with components v1 and v2, then the dot product u dot v is equal to u1 times v1 plus u2 times v2. So we multiply the corresponding components and then we sum them. So for example, if we're given the vector u with entries 4, 2 and the vector v with entries 1, 3, then u dot v will be equal to 4 times 1 plus 2 times 3. So we get 4 plus 6 and that is equal to 10. So the dot product of u and v is equal to 10. A scalar. So now we have some properties of the dot product. So if we let u, v, and w be vectors in the plane and we let c be a scalar, then the following properties will hold. So for the first one, we have u dot v is equal to v dot u. So that is the commutative property. For the second one, we have 0 dot v is equal to 0. So we have a vector with all 0 components dot v is equal to 0. So that's analogous to the 0 property of multiplication. Now for the third property, we have u dot and then in parentheses v plus w is equal to u dot v plus u dot w. So this is the distributive property. Now for the fourth one, we have v dot v is equal to the magnitude of v squared. So any dot product of a vector and itself, we just find the magnitude and then we square it. And then for the last property, we have c times u dot v is equal to c times u dot v, and that is equal to u dot c times v. And this is the associative property. Here we're given some vectors and we're told to find the following quantities. So for the first example, we need to find the dot product between u and v and multiply that scalar by the vector w. So first we find the dot product of u and v, so we multiply each of the corresponding components. So negative 2 times 4 will give us negative 8. And now 6 times negative 8 gives us negative 48. So then negative 8 plus negative 48 gives us negative 56. Now we can multiply that constant by each of the entries in the vector w. So then we have negative 56 times 2 gives us negative 112. And negative 56 times negative 4 will give us 224. Now for part B, we are told to find the dot product of u and 2v. So now using our property that u dot 2v is equal to 2 times u dot v, then we can just substitute our u dot v for what we just found, so that was negative 56, and multiply by 2, so we get negative 112. Now for part C, we are told to find the magnitude of u. So you can just square each of the entries and add them, and that is equal to 40, and then we take the square root. So the angle between any two non-zero vectors is theta, where theta is greater than or equal to 0 and less than or equal to pi. So we can find that angle theta by this following formula. So the cosine of theta is equal to u dot v divided by the product of each of their magnitudes. So the magnitude of u times the magnitude of v. So on the numerator we have the dot product, and in the denominator we have the product of magnitudes of both of their the vectors. So here we have an alternative form. So we are just isolating the u dot v. So we just multiply by the magnitudes of u and v on both sides to get u dot v by itself on the left hand side. So there are 5 possible orientations of the two vectors. The first one being they are going in opposite directions. So that happens when cosine of theta is equal to negative 1. So that means theta is equal to pi. For the second orientation is when the two vectors form an obtuse angle. So that happens when cosine of theta is greater than -1 and less than 0. And that happens when theta is greater than pi over 2 and less than pi. Now, the third possible orientation is when the two vectors form a 90-degree angle. And that happens when cosine of theta is equal to 0. So that means that theta is equal to pi over 2. Now, the two vectors can also form an acute angle. And that happens when cosine of theta is greater than 0 and less than 1. And that happens when theta is greater than 0 and less than pi over 2. And then lastly, the two vectors can be going in the same direction, and that happens when cosine of theta is equal to 1, which implies that theta is equal to 0 for that case. Now we obtain an orthogonal vector if and only if the dot product of the vector u and v is 0. So u dot v is equal to 0. So the term orthogonal means the same as the term perpendicular because the orthogonal vector meets at a right angle. This definition includes the 0 vector since 0 dot u is equal to 0. So here we're determining whether the vectors u and v are orthogonal, and we do so by computing the dot product, and if that is equal to 0, then they are orthogonal. So first we multiply each of the corresponding components, so 2 times -3 and 3 times 2. Then we sum those products, so -6 plus 6 is equal to 0. And because that is equal to 0, the vectors are orthogonal. So that means that the two vectors have a 90-degree angle between them. If we let u and v be non-zero vectors such that u is equal to w1 plus w2, where w1 and w2 are orthogonal, and w1 is parallel or a scalar multiple of v. So we see right here we have v, and then w1 right here is parallel to v, or a scalar multiple. Here we have v, and w1 is parallel or a scalar multiple. Then the vectors w1 and w2 are vector components of u, and the vector w1 is a projection of u onto v, and it is denoted right here. So w1 is equal to the projection of u onto v. Then we can find the vector w2, and that is given by the vector u minus w1. And just to show w1 and w2 are orthogonal, we see right here is w2 and w1. They form a 90-degree angle, and then w2 and w1. So the projection of u onto v is given by this formula to the right-hand side. So if you let u and v be non-zero vectors, then the projection of u onto v is given by, so in the numerator we have the dot product of u and v, in the denominator we have the magnitude of v squared, and then we are multiplying by the vector v. So that gives us the projection of u onto v. So now on the left-hand side we are finding the component w2, and then first we need to find the projection of u onto v, and then doing so we follow these steps. So first we have u is equal to w1 plus w2. We said those two were the components of u. Now we know that w1 is a scalar multiple of v, so we can plug in c times v for w1. So now we have u is equal to c times v plus w2. So now we can take the dot product of each side, so we'll have u dot v, and then we'll have c times v plus w2 dot v. So now we know that the dot product between a vector and itself is its magnitude squared, so that's how we get that portion. And we know that w2 dot v gives 0 since they are orthogonal, so that's why we get that portion right there. So now solving for the scalar, we just divide by c on both hand sides. Sorry, we divide by the magnitude of v squared. So now on the right hand side it can cancel out, and that is how we got this expression. The scalar is equal to u dot v divided by the magnitude of v squared. Now to find w1, we can multiply c times v, and we stated that c was equal to this expression, so we just plug it in there, and then multiply by our vector v. Now in this example we'll be finding the components of a vector that has a length of 5 and points at an angle of 36.87 degrees above the horizontal axis. So our first step is to find the horizontal component. So we know that our vector v is equal to the magnitude of v times the cosine of theta in the horizontal direction plus the magnitude of v times the sine of theta in the vertical direction. So we have the length 5, and we are given the angle 36.87, so we plug that in for cosine of theta, so cosine of 36.87. So cosine of 36.87 is 0.799, or rounded up is equal to 0.8 right here. So now we have 5 times 0.8, and that is equal to 4. Now for the vertical component, we do 5 times, now this time we do sine. So sine of 36.87 is equal to 0.6, so now we have 5 times 0.6, and that is equal to 3. So in our linear combination form, we have v is equal to 4i plus 3j. And then in this example, we were denoting everything in terms of a. So our vector in component form, a is equal to 4 comma 3. So this is our vector right here, a. So for the x component, we have 4. And for the y component, we had 3. A constant force F acting along a line of motion is known as work. So it can be determined by the magnitude of the force times the distance. So we have the magnitude of F, our vector, and the distance given by the initial point P and terminal point Q. Now, if the force is not directed along the line of motion, the work done is given by the equation below. So work is equal to the cosine of theta times the magnitude of the force times the distance. So theta is the angle between the line of motion and the magnitude of the force. So given the formula in the previous slide, we will be going over how to determine the work. So we are imagining that we're pulling a child on a sled. Your pull on the rope has a force of 50 newtons. So that is given by this vector right here. And the rope has an angle of 60 degrees, so right here. Now, relative to the flat ground. And you're pulling the sled forward for 10 meters, so our distance is equal to 10. So the force should be along this line because we're seeing that it has an angle of 60 degrees. So now using the formula, we have work is equal to the cosine of theta times the force times the distance. So we're given 60 degrees for theta. We had a force of 50 newtons and a distance of 10 meters right here. So cosine of 60 degrees is equal to 1/2. So we have 1/2 times 50, which we can just write 25. And then 25 times 10 gives us 250 right here. So then since our units were newtons and meters, so 1 Newton meter is equal to 1 joule. So then we have 250 joules is the work that we have done in this example.